In previous videos, we've discussed how to take several approximations to some quantity R, none of which are very good, and combine them to get a much improved estimate. See the preceding ones for details on how to calculate E, F, G, H, I, and J. The key points is by taking combinations of the original approximations based on H over 2, H over 4, and H over 8, we can, in this column of numbers, obtain approximations whose error term starts off not with H to the first, but with H squared instead. In E, F, and G, the error term contains no H to the first power term. H and I contain no H to the squared term. This has no H cubed term. For that reason, I'm going to invent some labels for these numbers. In the columns that contain no H to the first power, I'll call that column with index 1, and it's usual to use K for the column index. When I don't have any H to the first or H squared terms, I'll call that K equal 2, and the last column here will be K equal 3. We also have, though, a column of numbers that are approximations. No terms H to a power have been eliminated yet in those approximations, so I'll call that column with index K equal 0. I'll have to approximate little a, little b, little c, little d values using whatever my approximation method is. So I'll have to figure out column K equals 0 separately. After I do that, though, in each successive column, there'll be one fewer thing to calculate. If you'll recall the pattern, this number is obtained by multiplying this number by 2 to the first power, subtracting that number, and dividing by 2 to the first power minus 1, which I'm going to keep saying even though that number is 1. This number is 2 to the first power times that, minus that, divided by 2 to the first power minus 1 again, likewise for G. To take these three approximations and eliminate the H squared term, I multiply the number immediately to the left by 2 squared, subtract that number, and divide the result by 2 squared minus 1, which is 3. Likewise, to get I, I'll calculate 2 squared times G minus F divided by 2 squared minus 1. And lastly, to get J, I'll multiply I by 2 cubed, I'll subtract H, and then I'll divide that number by 2 cubed minus 1. The power that goes with the 2 to a power, is the same as the column index, 1, 2, and 3 in this case. I'll index the rows, the horizontal rows, with indexes 0, 1, 2, and 3 in this case. If you'll notice, 2 to the third power is 8, 2 squared is 4, 2 to the first power is 2, H is H divided by 1, which is H divided by 2 to the 0 power. In this initial column, I can think of my approximations as being the approximation method A based on a spacing H divided by 2 raised to the I power, where I is the row index that goes with the individual approximations. I'm going to make up a symbol for all of these different numbers. By Tij, I mean the number that is in this table that corresponds to a certain first index and a certain second index. So, for example, if I were 3 and k, or the second index j, was 2, we would be talking about that number. When I write all of these numbers in terms of the T symbols, my table, that's what the T is for, now looks like this. These numbers I have to calculate using whatever my approximation method is, and the rest of them are calculated using our plan. So let's assume that I've already calculated these initial numbers in column k equals 0. How do I get the rest of them? Tik is 2 raised to the k power times the number that's immediately to the left of Tik. That would be t, still in row number I, but the previous column. I have to subtract away the number in the table that's immediately above Ti, comma, k minus 1, so I'll still be in the same column, but one row less. And then I have to divide by 1 less than the power of 2 that I'm using. Having calculated the initial column, when I'm calculating column k equal 1, I have to do this procedure for I equals 1, 2, and 3. When I'm working on column k equals 2, I have to do this for rows 2 for the row index and 3 for the row index. And lastly, there's only one number to calculate. So having selected some initial spacing, h, I'll generate the numbers that are in column k equals 0 of my table by using the approximation based on h divided by 2 to the I power, which will be stored into location row index I, column index 0 of my table. In view of what we were talking about a moment ago, I can write down lines of pseudocode to calculate all the other relevant numbers in the T table. This is pseudocode for my Richardson's extrapolation method. We have shown by hand, in a certain sense, that when we do column k equal 1 of this, we eliminate the h to the first power term. We have shown that by doing this, when we do column k equal 2, we eliminate the h squared term, but that's all we have literally convinced ourselves of. We think that this algorithm will produce numbers that are increasingly accurate in terms of the power of h, but this is just a conjecture at this stage. In order to convince ourselves that what's going on is what we think's going on, we're going to have to make a little side trip and talk about a proof method called the principle of mathematical induction. Once we know that, we will be able to prove our conjecture that as we construct more and more columns in this T table, more and more powers of h are removed from the error term, and things will actually go our way. So the next thing I'm going to talk about in my summer rambling here is mathematical induction. Until then, I hope everybody has a good day, and I'll talk to you again soon.